Hello students, in the previous video we have learned the concept of motion along a straight line and the physical quantities like distance, displacement, speed, velocity and acceleration. Today we are going to learn the graphical representation of motion. You know that the graphs they provide a convenient method to present basic information about a variety of events. For example, in maths you have studied a straight line graph helps in solving a linear equation having two variables. Here, to describe the motion of an object, we can use the line graphs. In this case, the line graphs, they show dependence of one physical quantity such as distance or velocity on another quantity such as time. So here we are going to study two graphs, that is distance versus time graph, its uses, and the velocity versus time graph and its uses. So you know how to draw a graph. When you draw the graph, you know that the independent quantity, it is always taken along the x-axis and the dependent quantity is taken along the y-axis. First we can discuss about the distance versus time graph. In distance versus time graph, the time is taken along the x-axis and the distance along the y-axis. So, the change in position of an object with time, it can be represented on the distance versus time graph, adopting a convenient scale of the choice. So, what is there? The change in position of an object with time. It can be represented on the distance versus time graph. And distance versus time graph, it can be employed under various conditions where objects move with uniform speed, non-uniform speed, or the object remain at rest. We can draw the distance versus time graph for objects which are moving with uniform speed, non-uniform speed or accelerated motion, or any object that remain at rest. Is that clear? Now, what is the use of the distance versus time graph? That we will discuss afterwards. Using distance versus time graph, we can determine the speed of an object. Now, see here. Here one graph is given in which the time in minute is taken along the x-axis and the distance in kilometer taken along the y-axis. And here x-axis, I already told you, time is taken, y-axis distance is taken. See how it is marked in x-axis. See, origin, then 20 minutes, 40 minutes, 60 minutes, and y-axis 10, 20, 30, 40 kilometers. How the objects move, that is, it covers equal distance in equal interval of time. That we can find it out. And see the shape of the graph. The shape of the graph, it's a straight line. And this indicates uniform speed. So from this it's clear that the distance versus time graph of an object moving with uniform speed, it's a straight line. Is that clear? And now see the graph, the OB. The graph, the straight line graph is represented as OB. And the portion OB of the graph, it shows the distance is increasing at uniform rate. From the graph it's very clear. As the time passes on, the distance also increases, that also in uniform rate. And see here, instead of this uniform speed, we can use the term uniform velocity if you take displacement along the y-axis in place of distance. Is that clear to you? So now, already I told you, distance versus time graph can be used to determine the speed of an object. From this graph, see how the speed of the object moving with uniform speed, it is determined with the help of the distance versus time graph. Now for that, in the graph OB, take a small portion, that is AB. See the graph, it is already marked there, a small portion AB. Then what you have to do is, draw a line parallel to the x-axis from the point A and another line parallel to the y-axis from the point B. Is that clear? Now, these two lines, we can see they meet at the point C. So the line which is parallel to the x-axis, that is drawn through the point A, and the line parallel to the y-axis drawn through the point B, they both meet at the point C. And there you get one triangle, that is triangle ABC. Okay, now on the graph, see the portion AC. AC denotes the time interval, that is T2 minus T1. How will you get it? See the line that reaches the x-axis, the dotted line from C and from A? Yes, that is T2 minus T1. The portion AC represents T2 minus T1, whereas the BC, see the portion BC, it corresponds to the distance S2 minus S1. B is S2 and C point S1. So the BC portion represents S2 minus S1. And from the graph, we can see that as the object moves from the point A to B, see the graph, it covers a distance of S2 minus S1 in time T2 minus T1. Is that clear? Now, how can you find out the speed? You know that speed is equal to distance travelled upon time taken. So here the distance travelled S2 minus S1, the time taken T2 minus T1. Therefore, speed V can be calculated as S2 minus S1 upon T2 minus T1 from the graph. Is that clear? Now, this graph, it can be plotted. That means distance versus time graph can be plotted even for accelerated motion also. That for which one? Non-uniform motion. So here see this graph. This is the graph of non-uniform motion or accelerated motion. See the shape of the graph. It's not a straight line and it's a curved line, and that shows non-uniform speed or accelerated motion. Is that clear? So about distance versus time graph. Okay, distance versus time graph. For an object moving with uniform speed, it's a straight line. And for non-uniform speed or accelerated motion, it is not a straight line. Instead, it's a curved line. And use of distance versus time graph, we can use it for finding the speed of an object. I hope it's clear to you. So the next it is velocity versus time graph. As we have already seen in distance versus time graph, distance is taken along the y-axis and time taken along the x-axis. But in velocity versus time graph, time, as it is the independent quantity, it is taken along the x-axis, and the dependent quantity, that is velocity, taken along the y-axis. Here one sample of the velocity versus time graph, it is shown there. So, the variation in velocity with time for an object moving in a straight line, it can be represented by velocity versus time graph. So, for what velocity versus time graph it is used? The change in velocity or the variation in velocity with time for an object moving in a straight line. It can be represented with the help of the velocity versus time graph. Is that clear to you? Then, and if the object moves at uniform velocity, the height of its velocity versus time graph will not change with time, and it will be a straight line parallel to the x-axis. See that this graph you see here, see that as the time passes, the velocity remains the same. See the time for 1 hour, 2 hour, 3 hour, 4 hours. But see the velocity which is shown there. It is steady at 40 km per hour. So the graph, it is a straight line which is parallel to the x-axis. So as the time passes, then also the velocity remains the same. So for uniform motion of any object, the velocity versus time graph is a straight line parallel to the x-axis. Is that clear? Now, and the velocity versus time graph, it can be used to find out the magnitude of displacement. How can you find it out? The area which is enclosed by the velocity versus time graph and the time axis, it will be equal to the magnitude of displacement. So the area enclosed by the graph, that gives you the magnitude of displacement. And using velocity versus time graph, we can also study the uniformly accelerated motion. Now, see here which is the area enclosed? That is a shaded portion you can see. That's the area enclosed by the graph. It's the shape of a rectangle. And if you find out this area, that will give you the magnitude of displacement. Is that clear to you? Okay. From this, you can see the object, I told you, it's moving with uniform velocity because the velocity is not changing, it's remaining at 40 only. And we have seen that the graph is a straight line which is parallel to the x-axis. Now, the area which is enclosed by the graph, that's equal to, what is the shape of the figure? The shaded region, that is rectangle. So the area of the enclosed, the shaded portion, that will be the area of the rectangle ABDC. How to find out the area of rectangle? Area of rectangle is equal to length into breadth. Here it can be written as AC into CD. That's equal to AC into CD. And what is AC? AC from C to A, how much it is? That is 40. That is 40 multiplied by T2 minus T1. AC multiplied by CD, that is 40 multiplied by T2 minus T1. That is the area of the rectangle ABDC. Is that clear? So from velocity versus time graph, we get the magnitude of displacement. And also we can study about uniformly accelerated motion by plotting velocity versus time graph. I hope it's clear to you. Now next, see the next graph. This is the velocity versus time graph of an object which is in uniform acceleration. See, from the graph itself it's clear. As the time passes, see, what about the velocity there? Velocity goes on increasing. The velocity keeps on increasing. And in this graph, the distance traveled by the object is given by which area? See that? A, B, yes, C, D, E. The area, when I read it, you listen to that points A, B, C, D, E. It includes one rectangle and one triangle. So how will you get the area of the enclosed region? That will be area of the rectangle ABCD plus area of the triangle ADE. You know how to find out area of rectangle. That is AB into BC, yes, plus AD into DE divided by 2. Isn't it? Because you know that area of triangle half into base into height. Otherwise half into AD into DE. So once again listen, in this graph, this is a graph of an object moving with uniform acceleration. That is, as the time passes, the velocity goes on increasing. So here also take a small portion AE. So the magnitude of the displacement or the distance travelled S can be calculated by finding out the area of the region ABCDE. ABCD region includes one rectangle and one triangle. So the area is equal to area of rectangle ABCD plus area of triangle ADE. That's equal to AB into BC plus half into AD into DE. That will give you the area. We can substitute the values. Is that clear? What is AB? Just listen, what is AB? AB is equal to 20. What is BC? T2 minus, yes, T1. And next, half into what is AD? Same, T2 minus T1. And what about DE? DE, that is just above 30 it is, okay, around 32 minus that 19 or 18 like that. So see that dotted line where it reaches, you can note down the point or the velocity and can be calculated. Is that clear? So that's all about velocity versus time graph. And these two graphs also. Just you listen. Here see, this is the graph of, this is a velocity versus time graph only, in which you see the velocity is decreasing with time. See, from 20, isn't it? As the time passes, the velocity goes on decreasing. But the next one, see, here it's a graph of non-uniform variation of velocity with time, because velocity sometimes it increases, sometimes it decreases. So it's not uniform. The velocity is not uniform. That's all about distance versus time graph and velocity versus time graph. I hope that portion is clear to you. So next we can study the next type of motion, that is uniform circular motion. So what is circular motion? If the object moves in a circular path, and that motion is called circular motion. And you know that when the velocity of an object changes, we can say that the object, it is accelerating, or there is an acceleration. And the change in velocity, it could be due to the change in magnitude, or the change in the direction of the object, or change in both. So how the velocity of an object can be changed, we have already learned it. How the velocity can be changed, either by changing the speed, or by changing the direction of motion, or by changing both speed and direction of motion. Is that clear to you? Now, see here that picture, what it is shown there. Here, the first picture, it shows what is the shape it is? Rectangular. So it shows the path of an athlete along a rectangular track ABCD, isn't it? An athlete is running along a rectangular park. See that the athlete runs at uniform speed on the straight parts, isn't it? When he runs, he can run in uniform speed in the straight parts, that is AB, BC, CD and DA of the track. But in order to keep himself on track, he quickly changes his speed at the corners. When he comes to the corners, he has changed the speed. And you know how many times when the athlete have to change his direction of motion while he completes one round? To complete one round, how many times he has to change the direction? It's very easy. How many times? 4 times. But is that clear? In the second one you see, it's a hexagonal shape. Rectangular shape he changed 4 times. Hexagonal means how many sides or how many corners? 6. So how many times he has to change the direction? That is, he has to change 6 times while he completes one round. And if it is an octagonal shaped track, 8 corners or 8 sides. How many times he will change? That is 8 times, isn't it? And next one, see, that is the circular one. If the athlete moves with a velocity of constant magnitude along the circular path, the only change in velocity is due to the change in direction of motion, isn't it? In circular path, when he moves, the velocity changes only due to what? Only due to the change in direction. Here the speed remains the same. And the motion of the athlete moving along a circular path, it is an example of accelerated motion. Clear to you? Why accelerated motion? Because as there is a change in direction, even though the speed remains the same, there is a change in direction. You know that then there is a change in velocity. Whenever there is a change in velocity, there is an acceleration. So we can say that the motion of any object along a circular path is an example of accelerated motion. Is that clear to you? And in accelerated motion or in the movement along a circular path, you know the circumference of a circle is given by the formula 2 pi r. What is circumference? The total length, isn't it? So in rectangle, quadrilateral, we say perimeter, the total length of all the sides. But here it is the circumference. And then how can you find out the speed or the velocity here? How can you find out the velocity here? That is the circumference upon the time taken. Here suppose if the object takes t seconds to complete one round along the circular path having radius r, then the speed of the object, that is v, is equal to 2 pi r upon t. And here when the object moves in a circular path with uniform speed, the motion is called uniform circular motion. See here, I told uniform speed, not uniform velocity. Speed remains the same, but velocity is not the same. Why? Because there is a change in direction. So in uniform circular motion, what is it? The speed is the same, but velocity is not the same. Is that clear? So what is uniform circular motion then? When an object moves in a circular path with uniform speed, then that motion is called uniform circular motion, and the speed can be calculated by the formula 2 pi r upon t, where r is the radius of the circle and t is the time taken. I hope that topic is clear to you. And another example for uniform circular motion, you know that the motion of the fan, isn't it? That is ceiling fan. It is an example of uniform circular motion. And another one, a stone. See that picture here? when you rotate a stone with the help of a string. It is an example of uniform circular motion. A stone which is describing a circular path with a velocity of constant magnitude. See that velocity of constant magnitude. Magnitude of velocity means it's the speed. So with constant speed. And see here this picture you see. When the stone is released, in which direction it moves? So when you rotate a stone with the help of a string, and at a certain point when you release the stone, it will go in the direction of the tangent. It moves along a straight line tangential to the circular path. See that the first picture it is shown there. When it is released, it moves along the tangent. Second one also see, it moves along the tangent. So these are examples of uniform circular motion. And there are many more examples of objects moving under uniform circular motion, such as the motion of the moon and the earth, a satellite in a circular orbit around the earth, and even a cyclist on a circular track at constant speed. All these are examples of uniform circular motion. I hope what we have discussed today is clear to you. In the next class, we are going to study equations of motion. So we will derive the equations of motion. Here one assignment I can give you from this graph, that is in your textbook, page number 104. There is one table given, that is table 8.2. You can draw a graph using the table there. Same way, one more graph you can draw, that is from page 106, and then from page 107. Activity 8.9, that is table 8.4, and activity 8.10, that is table 8.5. So 3 graphs you draw in a graph paper and stick that page to your notebook. Okay, thank you.